we're now going to take a look at the concept called specific heat and see how it can be used in calculations that will enable us to, for instance, calculate the amount of energy contained in a sample of a food product like cottage cheese, which we looked at in our previous video. So specific heat refers to the relationship between the amount of heat a substance absorbs and the temperature increase that results. We already have some appreciation of specific heat just by observation in the world around us. I'm holding up a metal pot in my hand that I got from our kitchen. Cookware has traditionally been made out of metal because metals generally have very low specific heats, or relatively low, I should say, specific heats, meaning that a small amount of heat absorbed by the metal will cause its temperature to increase readily. So metals have low specific heats, while insulators have high specific heat values, meaning that it takes a lot of heat that must be absorbed by the substance in order for its temperature to change. So when I have this pot on the stove, I know that the pot itself, the metal portion, is too hot for me to touch after it has absorbed any appreciable amount of heat. But I will pick the pot up by its insulated handle. Even when the metal is hot, I'm not worried about burning my hand on the handle because the handle is coated with an insulator, a material that has a high specific heat value, so its temperature hasn't increased that much even in the presence of heat being applied. The specific definition of specific heat is the amount of heat or energy, heat is a form of energy, needed to increase the temperature of exactly 1 gram of a substance by exactly 1 degree Celsius. So if you take a look at all of the substances or all of the terms that are used, we have heat, we have mass, we have temperature. So the units of specific heat are going to reflect all of those concepts. Either joules per gram degree Celsius or calories per gram degree Celsius are the typical units of specific heat. Specific heats are physical properties of substances, and if you turn to page 80, table 3.11 in the Chem 2A text, or a similar table in virtually all introductory general chemistry textbooks, you'll see that the table lists specific heats for various substances. And I see aluminum and copper and gold and iron listed here, and their specific heats are much lower than the specific heat of water, which is 4.184 joules per gram degree Celsius. Notice that water's specific heat is the only one that I'm asking you to memorize. And of course, it's very easy to memorize it because the value in either joules or calories is equal to the conversion factor between joules and calories. 4.184 joules equals 1 calorie, and those values per gram degree Celsius correlate to the specific heat of water. So specific heats are physical properties like densities. If you need a specific heat for a substance, you simply look it up from a table or from a handbook or find it online. So we can do calculations involving specific heat that can enable us to calculate either the heat gained or absorbed by a substance related to its mass, its specific heat, and its temperature change. So here is our general equation. Heat equals mass times specific heat times temperature change. And using symbols to represent that, heat is represented by the symbol Q, mass with M, specific heat, SH, and temperature change with this triangle shape, which is the Greek letter delta for change, delta T, change in temperature. So you can use this equation to calculate any one of the variables involved in it, either heat or mass or specific heat or temperature change. Let's do an illustration with a problem involving titanium metal. 2.31 kilojoules of heat is absorbed by a sample of titanium metal at 42 degrees Celsius, causing its temperature to rise to 65.8 degrees Celsius. What is the mass of the titanium metal in grams? So we are going to do this calculation. Specific heat calculations have a lot of numbers and data involved. So I strongly suggest that you read through the problem, label all the data that is listed with the appropriate units. For example, the first number we come to is a heat value, 2.31 kilojoules of heat. Well, that's our Q in our equation. So I am labeling Q equals 2.31 kilojoules. But then I am noting right here that kilojoules is not one of the units involved in the specific heat value. So I'm going to have a dimensional analysis problem if I leave that value in kilojoules, because specific heats are in either joules per gram degree Celsius or calories per gram degree Celsius. So as soon as I see that Q is in kilojoules, I'm going to quickly do the conversion that we learned in Unit 1, converting from kilojoules to joules. 1,000 joules is equal to 1 kilojoules, and get the value in joules, which now is 2.31 times 10 to the third kilojoules. The titanium metal was initially at 42 degrees Celsius. So as I've labeled here, that's our beginning or initial temperature. When it absorbs the heat, when a substance absorbs heat, its temperature increases. So its temperature rises to 65.8 degrees Celsius. That's the final temperature. And knowing the initial and final temperatures, we can calculate our temperature change. So our change in temperature is going to be our final temperature minus subtracting the initial temperature from it, and we calculate a delta T of 23.8 degrees Celsius. And you should double check me on that. 23.8 degrees Celsius doing the subtraction. Right, so what have we figured out so far? We have figured out our Q. That was given, I should say. We know what Q is. We have calculated our delta T. We're trying to solve for mass. That means we're going to have to know the specific heat of titanium. And notice the specific heat of titanium was not stated in the problem. Why was that? Because this problem is testing, do you know this general equation? Do you know you need the specific heat? Do you understand that it is a physical property and that you can look it up from a table? So I'm going to page 80, looking at table 3.11, finding titanium, making sure that I am choosing the right value with the right unit. For the data that I have, given that my heat value is in joules, I need to use the titanium value with units of joules per gram degree Celsius. And when I look up the specific heat of titanium off the table, I find that it is 0.523 joules per gram degree Celsius. So I see I have my Q value, my heat value. I have my specific heat value. I have my change in temperature value, my delta T. In other words, I have Q, I have my specific heat, I have my delta T. I should be able to solve this equation for the mass of titanium. So here is our general equation. Q equals mass times specific heat times temperature change. And we're going to solve it for the variable we need, which is mass. So using some algebra skills here, basic algebra, dividing both sides of the equation by specific heat and delta T, I come up with mass equals Q times 1 over specific heat times 1 over delta T. And once I have this equation, I can then plug in the data that I've labeled here carefully to the left of this problem. So plugging in to the left, from the data listed to the left, I get M, or mass, equals, my Q value is 2.31 times 10 to the third joules. 1 over specific heat means take that specific heat and write it in its flipped or inverted form. So I'm taking the specific heat and writing it in its flipped or inverted form. Why do I need to do that? So that I immediately see how the dimensional analysis is working. If I don't write it in this way, I'm going to have stacking of units several layers deep, and that is always difficult to unpack and analyze. So I'm writing my specific heat in its flipped form. I see that my joules are canceling. I'm writing my temperature change as 1 over delta T, or 1 over 23.8 degrees Celsius. I see that my degrees Celsius unit is canceling, and I see that the last unit left in the problem is grams in the numerator, which is exactly what we're asked to solve for. What is the mass of this sample in grams? So taking my calculator and going through the calculation, and after I do it once, I am going to double check it again to see if I have the right answer. I get 186 grams of titanium as the mass. And let's just do that double check. It's very easy to hit an incorrect button and have the incorrect answer. So it is always a good idea to repeat the calculation and make sure you get the same result twice. And I do get the same result twice. Checking my sig figs, I see that my heat value has 3 sig figs. My specific heat, which is a measured value, has 3 sig figs. My temperature change has 3 sig figs. So my answer should have 3 sig figs. The mass of the titanium sample is 186 grams.